So 10-4, we're talking about the determinant of a square matrix. We've already done a determinant of a 2x2. It was really brief, and we calculated the determinant in order to find the inverse of a matrix. The determinant is actually a part of it. Okay. So for this section, we're going to find the determinant of 2x2 matrices. We're going to talk about things called minors and cofactors. Guys, I'm going to be totally honest with you. I have never dealt with a cofactor in my life until going through this class. I don't care. I'm okay with minors, but this text does something called expansion by cofactors. I will show you the way that they do it in the text. That way, if you're looking at the notes or going back at the PowerPoints or whatever, you can follow what they did. I'm also going to show you the way that I've done it my entire life. Okay. You can only find the determinant on a square matrix, and we're only going to go up to a 3x3. We're not going to do a 4x4 or anything else. Okay. Hey, here we go. Every square matrix can be associated with a real number called its determinant. So if I have a square matrix, I can give you one number called the determinant that represents that matrix. They have many uses. We'll see some in this section, but we'll also come back to it in 10.5. Historically, the use of determinants arose from special number patterns that occur when systems of linear equations are solved. Okay, here's a system. System 1, ax plus by equals c with subscripts of 1s on the constants. Ax plus by equals c with 2s on there. The numbers just indicate different coefficients. To find the determinant, I'm going to take a1 times b2, that's the down diagonal, and subtract a2 times b1, that's the up diagonal. I could actually solve this system by using this information here. This is actually called Cramer's rule, and we'll talk about Cramer's rule in 10.5. But what I want you to see is the denominators on both of these. The denominator is the determinant of the original coefficient matrix. Okay. Again, a1 times b2, that's the down diagonal, minus a2 times b1, that's the up diagonal. We're going to take the product going down on the diagonal minus the product going up on the diagonal. I'm going to say this many, many times. Down minus up. Now, if down minus up equals 0, we have something divided by 0. What's that mean? Can't do it, right? Do you remember us talking about if the determinant was 0, there was no inverse? Because there was a formula for finding the inverse. And that formula was 1 over the determinant times swap the DNA, change the sign on the B and C. Y'all remember all this, right? It was just from Friday. I say it that way on purpose because you'll remember DNA. D and A. Exactly. I'm saying it like that on purpose. Swap your DNA. Okay, so here is a coefficient matrix. And the determinant of that matrix, so DET, determinant of matrix A, is equal to down diagonal, A times B, A1, B2, minus the up diagonal, A2, B1. Yay. Basically, this slide says the exact same thing. I can write determinant of A in several different ways. Okay, let me look at this right here. The matrix consists of these 4 elements. Matrix is written with brackets, right? Look down below. Are those brackets? No. If you see that, which is the same thing as, it looks like absolute value bars, that means calculate the determinant of the matrix. Okay? Calculate the determinant. The brackets mean this is a matrix. Okay? So here we go. Determinant can be written as determinant of A or looks like absolute value of A. Interchangeable. Doesn't matter how it's written. I want the determinant. Right here it says, although vertical bars are also used to denote the absolute value of a real number, the context will show which is intended. A conventional method for remembering the formula, the determinant of a 2 by 2 matrix is shown below. Ready? You do the down diagonal product, subtract the up diagonal product. Have I said that enough? Take the down diagonal product, subtract the up diagonal product. You take the down diagonal product and subtract the up diagonal product. Christian, can you say it in Spanish? Note the determinant is the difference. Here we go again. It's the difference, which means what? Subtract the products of the two diagonals. In example 1, you'll see that the determinant of a matrix can be positive, 0, or negative. Line along. If you have a 1 by 1 matrix, the number inside that matrix, that is the determinant. So if I had a 1 by 1 matrix consisting of -2, the determinant of that matrix is -2. Do what? Yeah, I don't know. Not right offhand. What? On the homework? Okay, here we go. Letter A, I want to calculate the determinant of A. I won't put those in parentheses like they do. The determinant of A. Okay, tell me. Okay. Subtract it from the up diagonal. No, not subtract it from.
You just subtract. You get the difference and subtract the up.
Now subtract the other one. Yeah. Subtract the upward. Okay, the upward diagonal is 1 times -3, right? I know, but he said subtract it from. I was like, whoa, we can't subtract it from anything because we don't have anything yet. Okay, so the answer to that would be 4 minus -3 would be +3, which is 7. Okay. Part B, I want the determinant of the matrix containing 2, 1, 4, 2. What do we get? Okay.
-4 times 1. So it's 0.
Perfect.
So 0 is the determinant?
Yes.
Okay.
0 is the determinant. Can we have a 0 determinant? Yes. Can we have a positive determinant? Yes. Can we have a negative determinant? Yes. It's when you take the down diagonal and you subtract. The determinant is useful for many things. We're going to talk about it specifically with Cramer's rule when using it to solve a system of equations. It's also used in the formula for calculating the inverse of a 2 by 2 matrix. Yes. It's the diagonal minus the up diagonal. Huh? Put it on your cheat sheet. There you go. Part C, I want the determinant of matrix C. Down diagonal, we get
0 times 4.
0 minus the up diagonal. 0 minus 3.
Yep.
Ta-da. Okay, questions on this? I'm going to slide right by the next couple real quick. If you want to screenshot them, fine, but I mean, it's just what we just did. There's that one. There's that one. And moving on. Okay, minors. Uh,
Is that an IJ?
I sub j, yes. I'm muting myself. Hello. Okay, I'm recording again. The campus cop. I don't know. Go to the office. So if A is a square matrix, well, that's the only ones that have determinants. Okay. Then the minor sub ij is determinant of the matrix obtained by ith row and the jth column from A. The cofactor C sub ij is the entry A sub ij is C sub ij is equal to -1 times M sub ij. The sign pattern for the cofactors at the left, which there's nothing there. Sit down.
There's none of that.
Okay, guys, this is wordy.
Yes.
Okay.
Try that.
All right.
All I heard was
Okay.
different letters.
Before I do the determinant using expansion by minor, I'm sorry, their way is expansion by cofactors. Let me show you the first way I learned how to find the determinant. So to find a determinant, it's the down diagonals minus the up diagonals. Have we heard this before? But notice I only have one diagonal. I got a problem here, don't I? So watch this. If I take column 1 and column 2, can I now do down columns or down diagonals? Okay. What is 0 times -1 times 1?
0.
0. What is 2 times 2 times 4?
8. Oh my gosh, 16. We need to go back to basic.
Okay. Since I'm doing down, I'm going to make them green. Okay. So you said this down
0.
was 0. This down was 16. And this down is
0.
okay. Because these are positive, right? The downs are positive, subtract the ups. I'm going to now subtract. Now let's go to the ups. Okay. 4 times -1 times 1. 0 times 2 times 0.
0.
1 times 3 times 2. Okay. I'm going to take 0 plus 16 plus 0 minus -4 minus 0 minus 6. Y'all go with that? All the downs were added. We subtract the ups, correct? Because I need to use all numbers in the diagonals. 3, 6, 9, that's all of them. Otherwise, if I use diagonals, I'm skipping these 3. So they're added over here so that I include them. And same thing with up diagonals. These get ignored. So I brought them over. They're used over there. So, columns. Yes. What'd you get?
14.
Good. The determinant of this matrix is 14. Now that's the first way that I was taught. I didn't show this the second period.
Why?
So, because that's not part of the curriculum. I'm just kind of expanding a little bit. After that, now let's talk about these minors. We're going to look at the main matrix. A equals 0, 2, 1, 3, -1, 2. I didn't make it big enough. 4, 0, 1. Okay. It says delete the first row and first column. So if I ignored the 0, 3, 4 and the 0, 2, 1, you see what's left?
Row echelon form?
Okay, no. Can you get a determinant of that? Down is
One.
1, up is
0.
1 minus 0 is?
1.
Okay, so the determinant based on the minor of the 0 is 1. Now let's use the 2. So I'm going to ignore this column and this row. 3 times 1, 4 times 2. 3 minus 8,
-5.
-5. I'm now going to go this way. 3 times 0, minus 4 times 1,
4, -4.
-4. Okay, so there are actually 9 minors to this one matrix. Okay, I've done 3 of them. I could now do the same thing. Ignore this row. That's kind of getting harder to do. Okay, ignoring that. See, that would give me this one. Is this making sense?
Mhm.
If I ignore a row and a column, I still have a 2 by 2 matrix left. Doesn't matter which row and column I eliminate, I'm left with a 2 by 2 matrix, right? No. If I wanted to get all of the members of the minor, yes. Okay. So if I was to do that, I think this shows it all. Nice. Nope. Oh, it's because, let me go back and go down. Okay. If I did this repeatedly, this matrix, the one that I started with, here are all the minors. Now, let me show you how you can calculate the determinant using expansion by minors, which is not what the book does. The book does expansion by cofactors, but I want to show you expansion by minors. Okay, to use expansion by minors, the best thing to do is to choose a row or a column, and it doesn't matter which one, but one that has a bunch of zeros or a bunch of ones, right? So this first row would be a good choice because it has a 0 and a 1. Okay. Row 3 would be a good choice, wouldn't it? Because it has a 0 and a 1 in it. The hardest one to do would probably be row 2. But regardless, you choose one row, okay, or column. So this column would be nice. But I like zeros and ones. So I would either choose row 1 or row 3. Y'all decide. I heard row 1 first. Row 1 or row 3 are virtually the same. Okay. Using expansion by minors or expansion by cofactors, we'll talk about that in a minute. This matrix is important. Any square matrix is going to alternate pluses and minuses. So if it was a 2 by 2 matrix of pluses and minuses, great, nice. A 2 by 2 matrix would look like this: plus, minus, minus, plus. Okay. The top left box is always going to be a plus, and then you just alternate from there. So I could go 4 by 4. That makes sense. Okay. So the way I would do the determinant by expansion by minors, y'all said row 1. All right, which means I'm on this row right here. I don't know what happened to the rest of the box down there. It just disappeared. Oh, there. Yeah, you're right. Okay. Going across row 1, the 0, I'm going to keep the sign of the 0. That's what the plus means. Plus means keep the sign. So I'm going to have 0. And if we cover that up, I've got times the determinant of -1, 2, 0, 1. Are you okay with that? Cover up the 0, see what's left.
Oh, okay.
I want the determinant of what's left. Okay. Minus. That means whatever, since I'm going across row 1, I want the opposite sign of this guy. So instead of 2, I'm going to write minus 2 times the determinant of this matrix. 3, 2, 4, 1. Y'all good? I'm ignoring that, everything that the 2 is in. Right? 3, 2, 4, 1. My next sign is a plus, which means keep the sign. So I'm going to keep this sign of a 1. So plus 1. What's left?
3, -1, 4, 0.
3, -1, 4, 0. Great. 0 times, I don't care. Okay. -2 times, what's the determinant of this guy? 3 times 1?
3,
Minus
-5.
3 minus 8, -5. Plus 1 times 3 times 0, 0. Minus 4,
1 plus
4. What is -2 times -5? Plus
4,
is,
14.
which is what we got a while ago.
I like the other two better.
Okay. Now let's talk about cofactors. In order to get cofactors, you first have to determine the minors. We've got the minors. And we found the minors by finding 9 different determinants. Okay? To convert minors to cofactors, we're going to use these signs. I'm going to the next slide. Yes. Here are my minors. My signs were plus, minus, plus, minus, plus, minus, plus, minus, plus, right? Okay. -1, leave the sign alone. -5, change the sign to 5. 4, keep the sign 4. So these signs don't mean that that answer is going to be positive or negative. Plus means keep the sign, minus means change the sign. Row 2, first guy, 2, change the sign, -2. -4, keep the sign, -4. -8, change the sign, +8. Are y'all following all that?
Yes.
Okay.
We say that it turns into negative because it's a negative, whenever there's a minus.
Well, clearly that's a positive number, right? Clearly. Okay. So, I mean, you might think of it as I'm multiplying by a +1, I'm multiplying by a -1, I'm multiplying by a +1, I'm multiplying by a -1, if that helps you. Okay. So anyway, we took matrix A, we found all the minors. We took the minors, applied our signs, came up with the cofactors. Now what they're going to do is they're going to use the cofactors and multiply them by matrix A. Okay. So the determinant, again, this is wordy. We can go through it or not. Okay. Go back. So what was my original matrix? Anybody have it handy?
0, 3, 4, going down.
One,
So 0, 2, 1, 3, 2, and then 4, 0, 1.
okay. To find the determinant using cofactors, we're going to just choose a row, choose a column. I don't care. What row or column?
Top one and the one all the way
We got to stay to get the same one. You want a row, you want a column, choose one. Choose one we haven't done yet. Row or column? Row, 1 through 3. Okay, row 3. So I'm going to take 4 times 5 plus 0 times 3. Y'all follow me? Plus 1 times negative 6. 4 times 5, 0 times 3, 1 times negative 6, 20 minus 6. There you go. Okay. But to get here, I had to do all of the minors, or just choose one row or one column. It doesn't matter, right? And then from the rows, I applied the signs to get the cofactors. What I'm doing when I do it is I apply the signs to the original matrix times the minors. Which way is the easiest? I like down diagonals, up diagonals. But easier than that, I'll talk about easier than that off recording.
Okay.
Okay. We got it was the same matrix every time, right? So the determinant better be the same every time, right? Okay. No, we've been doing the exact same thing. Okay. I don't even like this slide. Moving on. We've already done this. Okay. Find the determinant. Yay. Here's going across. Isn't that the same matrix?
Yeah.
Okay, we've already done this. Okay, there you go, 14. That is the end of 10-4.